So this section is on comets and asteroids, the debris of the solar system. There are two types of large objects in the solar system. Those are terrestrial planets and gas giants. And it turns out there are also two types of small objects, and those are asteroids and comets. First, we'll discuss asteroids, and then we'll discuss comets. Let me switch over and put up a few pictures. So that's a picture of a comet. Comet, when they're in the inner solar system, typically have two tails, but we'll come back to that. This is a sort of a picture of where the asteroids are. And so if you look at this picture, let me just see if I can zoom in just a little bit. What if we do that? I guess I can't. So if you look at the center here, there's the sun, and then just around that is Mercury's orbit, and then just around that is Venus's orbit, and just around that is Earth's orbit, and just around that is Mars's orbit. And then outside of Mars's orbit, you see all these dots for positions of asteroids. This between Mars and Jupiter. There are a few things to say about this. First of all, you can kind of see where that asteroid orbit is, but they kind of fall all over. They kind of fall all the way out to Jupiter. There's some that are inside the inner solar system in the area of the inner planets, and there are these clumps out here. The Greeks and the Trojans in the vicinity of Jupiter's orbit. You can see why maybe we think sometimes of the asteroid belt as a failed planet, because all this debris out here could have in fact coalesced into a planet, but for Jupiter's gravity. Jupiter formed too quickly and it kind of messed up in the same way that rings don't form into planets. Kind of Jupiter is preventing all these asteroids. A couple things to say about this. If you look at this picture, you might think, wow, there are a lot of asteroids. How can you possibly fly from the Earth through the asteroid belt to Jupiter and not hit an asteroid? And we'll talk about that. It turns out, well, it says here in the caption, here the asteroid dots are too big and give the false impression about how crowded it is. It would look, if you were in it, note that the addition of those in the asteroid belt, there's also an addition some along the lines of Jupiter's orbit. If these were actually put to their correct size, you wouldn't be able to see them here. They would be so tiny. And even asteroids as big as half a mile have about 1 million miles or more between them. So there's not much. It's not like you see in the movies where asteroids are very dense and spacecraft are having to dodge them. Let me switch back to the text for a minute. So here's a list of asteroids. Ceres is the largest one, so let's just talk about them for a minute. Year of discovery, 1801. I'll come back to that in a second. Orbit semi-major axis. Remember, Earth is about 1 astronomical unit. Mars is at about 1.5. So here is Ceres at 2.7. Jupiter is at 5. So that gives you some idea. Its diameter is 940 kilometers. That's maybe 550 miles. So if you remember, the Moon is about 2,000 miles in diameter. All of the asteroids put together, and they're on the order of 1 million or so, a few million, wouldn't add up to the mass of the Moon, of the Earth's Moon. So there's, even though it looks like a lot, it's not very much. And you can see there's some big ones here. These are the order in which they were found. And so Ceres, Pallas, Juno, Vesta. We can see these from Earth sometimes, if they're in the right position. We'll talk a little bit about their composition here in a minute, but there's a long list of these, and these come out of your book, so you can look at these if you want to at some point. Let me just... So it says, outline the history of the asteroids. So in the late 1700s, many astronomers thought there should be a planet between Mars and Jupiter because of the ratio of orbital radii. So I'm going to go back to this picture for a second and show you that if you look, there's a big gap there between Mars and Jupiter, and they noticed that. And one of the things they did was they calculated the ratio, you can see in this table, of the orbit of one planet to the orbit of the planet closer in. And so if you take 0.7 divided by 0.4, you get about 1.8. If you take 1 divided by 0.7, you get about 1.4. If you take 1.5 divided by 1, you get 1.5. If you take 5 divided by 1.5, that's Jupiter to Mars, you get 3.3. Everyone thought, well, that number looks kind of big. If there was a planet between those two, then they'd each be under 2. And so people started looking, largely for this reason, that when they mapped it out, it looked like there was a gap here for a planet. And in fact, they found them. They found Ceres in 1801, and by 1900 they had found 300. Now they're all tiny. Now we have more than 500,000 asteroids that have well-defined orbits. The average radius of the orbit is about 300 million miles, so about 3 astronomical units. So the circumference of the orbit, remember the circumference is 2 pi times the radius from your high school math. If the radius is 300 million, that makes 2 pi times 300 million gives you about 2 billion miles. If you divide that by 500,000, that's how many asteroids you have, you still get about 4,000 miles apart. But of course, that doesn't take into account the fact that they're spread out in terms of radius. And so it turns out that if you look at asteroids down to about a half a mile in size, half a mile in diameter, they average a few million miles apart. And so reasonably sized asteroids like that are not going to be super crowded, and even smaller ones are still very far apart. It's different in the movies. If you look in the movies, you get a completely different story. So let's talk a little bit about the composition of these asteroids. So let me go back to some pictures here. I'm going to have to swap this out a little bit. So I come over here. I'm going to page down. So there are 3 basic types. There's an S-type and a C-type and an M-type. And the S-type are called stony. They have silicon in them. Silicon is one of the minerals that we find in a lot of our rocks. C-type is they have carbon in them. So on the left side in this picture is closer to the sun, and on the right side is farther away. Carbon tends to form compounds at lower temperatures. It needs to be cooler to form solids typically, whereas silicon forms them at higher temperatures, rocks and things like that. And so the inner guys have more silicon in them, the outer guys have more carbon in them, but as you can see, there's a lot of overlap. Finally, the M-type is metal ones. And it's believed that the metal ones come from chemically differentiated asteroids where the metal sunk to the middle that were then collided and little metal pieces broke out of them. Most people who hunt asteroids, and you can do this on Earth, look for this type, because you can go get a metal detector and wave it over the ground and find metallic anything, coins, rings, that sort of thing. But you can also find asteroids, and they're not too hard to find. People find them pretty regularly. Just anywhere. They're equally likely to be anywhere on Earth, and so they just fall and hit the ground and they look like another rock, but you can find them with a metal detector. So the M-type usually comes from a chemically differentiated S-type or C-type that got hit and broken up, and the metal core came out and broke into pieces or something like that. So those are the 3 types. Let me go back. So C-type is carbonaceous, that's Ceres and Pallas. S-type is a stonier, they're a little darker. M-type, an example is Psyche. They're from the middle region, middle distance from the sun. Just scroll down a little bit here. So we've had a few missions to look at. I completely lost it. So we've had a few missions to study asteroids. S-type asteroid Ida. It has a moon named Dactyl, and so this literally has an asteroid with a smaller asteroid orbiting around it. Ida was studied by a flyby by the Galileo mission. Ida is about 50 kilometers or 30 miles in diameter, and dactyl is about 1 mile in diameter. Mars's moons Phobos and Deimos are probably captured asteroids. That's actually difficult to do, but Mars is in a good spot. If you're going to capture an asteroid, you would be Mars or Jupiter. Quite a few of Jupiter's moons, it's got 67 now, are probably captured asteroids. Not the big ones, not the big moons, not Io, Europa, Ganymede, and Callisto, but the other ones, some of the smaller ones. Phobos and Deimos were studied by the Viking mission, one of the early missions to land on Mars, and the Mars Global Surveyor from not too long ago. NEAR, which stands for Near Earth Asteroid Rendezvous, the spacecraft Shoemaker, went into orbit around Eros, which is an S-type, for a year, studying its surface composition. At the end of the mission, it landed on Eros and sent data for another week. So one of the things we've learned about asteroids is most of them are bags of gravel. So they've been battered so many times that rather than being like a solid thing, they're mostly bags of gravel, but some of them are sort of rock solid, and it just depends. And so Eros appears to be pretty solid. You've probably heard of movies or seen movies that involve us going out and defending ourselves against incoming asteroids, and you can Google any of these. Chelyabinsk in 2013 was 20 meters. You can look at it on YouTube. It was 500 kilotons, 30 times larger than the nuclear bombs of World War II. It had an air explosion. Lots of people got it on video because they had dash cams and stuff like that. If you just Google Chelyabinsk, you will find some interesting videos on it. In 1994, there was a 1,000-meter object that passed between us and the moon. That's still a long way away, 100,000 miles away or something like that. There was a big 40-meter one in Tunguska in Siberia that wiped out a forest. And you can Google that one too. World War I was going on at the time, or something like that. There was not quite, but it took us till after World War I to go look at it, if I recall correctly. And they were still the whole forest was wiped out. It was in a fairly unpopulated area. NASA tries very hard now to monitor what they call near-Earth objects, NEOs, and it wants to account for at least 90% of these. We now have about 1,000. These are just ones that are orbiting near the Earth. We want to be able to track their orbits so that if one happens to be likely to pass near the Earth, we'll be able to have enough time to do something about it. Estimates of 1 million near-Earth asteroids smaller than 1 kilometer but capable of wiping out a city. So fortunately we have computers that can start to watch for these things. But a lot of work has to be done. So I didn't list these, but what are the best approaches? So we want to be able to monitor these with computers, so that the computers can check on where they are and make predictions about how long, what the chances are they'll hit the Earth and when. And there's been a lot of interesting discussions for how to approach altering the course of an asteroid. And one is to just get it early. If you get it early, where it's a long way away, then you don't have to push it very hard early to make it miss. And so that's the sort of the best option. Blowing them up is not a really great option, because then you just have a whole lot more targets, and if it's pretty big, there are going to be some big chunks in there. It turns out that we get pieces of asteroids that land on Earth. Here is a piece of the asteroid Vesta. We call it a meteorite. So anything that's under a meter in diameter is called a meteoroid. If it travels into the Earth's atmosphere, it's then called a meteor. Sometimes we call that a shooting star. If it hits the surface of the Earth, it's a meteorite. And so that's why you hear meteorite. So meteoroid is a rock in space, smaller than a meter. If it's bigger than a meter, we typically call them asteroids, if they're from the inner solar system. And then if it's just shooting through the Earth's atmosphere, it's a meteor. The particles that shoot through the atmosphere when you see a shooting star are on average the size of a grain of sand. So even though they're bright, they're just something that was moving really fast that burned up. This meteorite is a piece of the asteroid Vesta. These are the pictures of Matilda, Gaspra, and Ida, the first three asteroids photographed from spacecraft flybys, printed on the same scale. You can see asteroids are beat up by impacts just like planets are. Everybody was out there bouncing around off each other. Gaspra is an S-type, Matilda is a C-type. Ida and Dactyl. So Dactyl is orbiting Ida, and you can see neither one of these is round. Ceres is the only round asteroid, so Ceres is the only one that gets to call itself a dwarf planet. We'll see that next, I think. No, not next. These are Phobos and Deimos. Mars' two small moons. They're only about 10 and 20 miles in diameter. They're not big at all, and they're certainly not round. They're both beat up by asteroids as well. This is the asteroid Eros. Here is Otakawa. This is Hayabusa, which separated, let's see, and the part at the right, this is the asteroid Itokawa. It was visited by the Japanese mission Hayabusa, which gathered some materials from it and returned to the Earth. So this package down here in the lower right is being returned or parachuted in, and the rest of the stuff is breaking up on reentry. Here is Vesta and Ceres. You can see Vesta is smaller, it's not round. Ceres is in fact round. You see this white spot, we're going to come back to that in a second. Here's the white spot. This made a big deal about 10 years ago. It turns out it looks like salt mines or something like that. Here's the picture of the Chelyabinsk meteor that passed through the atmosphere in 2013. This is the Tunguska results. So here are near-Earth asteroids discovered, and there's some interesting things in this graph. So this is the cumulative number discovered, and this is time. And of course, our ability to discover is steadily improving. But you notice that the ones larger than a kilometer in diameter, so the red, has sort of flattened off. So even though we're getting better at finding them, we're not finding very many anymore, which indicates that we probably have most of them. These are increasing sort of linearly in a straight line. The yellow ones, the ones that are more than 140 meters but less than a kilometer. And when you take into account the fact that our technique is getting better, this also means we're sort of starting to converge on some number. And finally, if you look at comets of all sizes, these are sort of still increasing. As our techniques get better, we're finding more and more. So they're all causes for concern, but we have good programs that are sort of watching them pretty carefully. And hopefully we're getting better and better at that. This is a near miss for Earth from 1992. But again, it's within 3 million miles, and the Earth is only 8,000 miles in diameter, so it missed us by a good bit. Nevertheless, we're watching these things. This would have done a lot of damage. A 5 kilometer, the one that wiped out the dinosaurs with, I think, 10 miles, only 3 times bigger than this. So it's something we would have to be very concerned about. All right, let's talk about comets.